Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 1. Introduction to Eigenvalue Problems and Properties. The eigenvalue problem is a fundamental concept in linear algebra and differential equations. It involves finding eigenvalues and eigenvectors of a matrix or a linear transformation. Eigenvalues and eigenvectors, also called eigenpairs, have a wide range of applications across different fields, helping solve real-world problems efficiently. The eigenvalues and the eigenvectors have a number of useful properties that make them an invaluable tool. Differential equations, whose eigenvalues and/or eigenvectors are sought, are called the eigenvalue problems or characteristic value problems. Eigenvalue problems are commonly encountered when solving mathematical models of various physical systems. A physical system can be expressed in terms of normal modes, which are the eigenvectors. Each normal mode oscillates at some frequency, which is basically an eigenvalue associated with the corresponding eigenvector. In some cases, only the largest, dominant, or the smallest eigenvalue, an absolute value, and its associated eigenvector may be of primary interest to an analyst. A matrix eigenvalue problem is defined as AX equals lambda x, where A is an by n square matrix, lambda is a scalar, i.e., eigenvalue, and x is the corresponding eigenvector of length n. We are interested in only the non-trivial, i.e., non-zero vector, solutions, which exist for some special lambda values of A, called eigenvalues. The solution of an eigenvalue problem involves finding a scalar vector pair, i.e., lambda and vector x. The eigenvalue problem can be expressed as follows, where I is the identity matrix and 0 in bold typeface is the zero vector. The eigenvalue problem has a non-trivial solution if the determinant of the resulting matrix A minus lambda I is 0, which gives Pn lambda, an nth degree polynomial called characteristic polynomial, or the characteristic equation, and lambda eigenvalues are the roots of the characteristic polynomial. Where are eigenvalues used? Physics and engineering, vibration analysis, stability of structures, machine learning, principal component analysis, differential equations, solving linear ordinary and partial differential equations, finance and economics, risk analysis, economic models, control systems, stability analysis in robotics and automation, Google PageRank, importance ranking of web pages, and so on. Property 1. The sum of all eigenvalues of A, including the repeated eigenvalues, is equal to the sum of the diagonal elements, i.e., the trace, of matrix A. Property 2. The product of all eigenvalues of matrix A is equal to the determinant of matrix A. Property 3. If A is a singular matrix, then at least one eigenvalue is 0. Note that in property 2, determinant of A is 0 for any lambda equals 0. Property 4. If matrix A has imaginary eigenvalues, they exist as complex conjugate pairs, i.e., lambda I equals ui plus and minus imaginary I times vi. Property 5. If matrix A is an upper or lower triangular matrix, then the eigenvalues of A are equal to the diagonal elements, i.e., lambda I equals aii. Property 6. For a non-zero beta scalar, if lambda and x are eigenpairs of a matrix A, then the eigenpairs of beta times matrix A are beta times lambda and just vector x. Property 7. If lambda x is an eigenpair of matrix A and M is a natural number, then the eigenpair of matrix A to the M is lambda to the M and just x. Property 8. If lambda x is an eigenpair of an invertible matrix A, then the eigenpair of inverse A is inverse lambda and just x. Property 9. If A is a diagonal matrix, then its eigenvalues are equal to the diagonal elements, i.e., lambda I equals dii, and its eigenvectors are the unit basis vectors for the corresponding ith column. Property 10. Eigenvectors of a matrix are linearly independent. That is, an eigenvector cannot be expressed as a linear sum of other eigenvectors. Property 11. If A has n independent eigenvectors, there exists a non-singular matrix P, where inverse P times A times P equals D is diagonal, and the matrix A is called a diagonalizable matrix. Estimating the location and bounds of eigenvalues is crucial in many applications because eigenvalues provide key insights into the behavior of matrices and systems. Stability analysis, engineering and control systems, computational efficiency, large matrices and numerical methods, bounding error in, approximate solutions, condition number, common eigenvalue bound techniques, Gerschgorin circle theorem, Rayleigh quotient, spectral graph theory, network analysis and data science, and so on. Some iterative methods for finding the eigenvalues require an estimate of the lower and upper bounds for the interval in which the eigenvalues lie. The Gerschgorin circle theorem provides a useful tool for estimating the eigenvalues of a matrix solely based on the matrix elements by constructing disks, Gerschgorin circles, in the complex plane. In the complex plane, a Gerschgorin circle with the center at AII and radius equal to the following, which can be defined for each row of A, the row index I equals 1 through n. The theorem states that every eigenvalue of A is enclosed by one Gerschgorin circle, where C denotes the complex plane. If M of these circles form a union set that is disjoint from the remaining n minus m circles, then D contains exactly M of A's eigenvalues. Since the eigenvalues of transpose A and matrix A are the same, we may also construct Gerschgorin circles by columns. Consider eigenvalues of A, a 6 by 6 matrix, in complex plane. Eigenvalues are real, thus, their centroids lie on real axis. Circle C4 encloses exactly one eigenvalue. D1 equals union of C5 and C6 contains two eigenvalues. D2 equals union of C1, C2, and C3 contains three eigenvalues. Let us consider the following 3 by 3 matrix. We would like to determine the Gerschgorin circles, that is, the bounds of each eigenvalue, and then find the eigenvalues using the characteristic equation. Each Gerschgorin disk is centered at AII with radius Ri, and all eigenvalues of matrix A lie within at least one of these disks. The Gerschgorin radius is found by evaluating the sum of the absolute values of the non-diagonal entries in a given row. We observed that the circle C3 encloses the circles C1 and C2, whose centroids are within circle C1. We can find the Gerschgorin disks with respect to columns. The radii are found by evaluating the sum of the absolute values of the non-diagonal entries in a given column J. where j is 1, 2, and 3. This alternative gives two circles with C2 enclosing C1. Both centroids are within the C1. Combining the results of the row-wise and column-wise circles, we are able to further narrow down the location and bounds of the eigenvalues. To find the eigenvalues, we find the characteristic polynomial, which is a third-degree polynomial. The roots can be obtained using a root-finding algorithm. We then find lambda equals 3 and a repeating root at lambda equals 4. It turns out that the roots are located in the union of circles C1 and C2. With this note, we conclude this lecture. That is all for now. See you next time with another topic. Bye.